So we emphasize the fact that we have endothermic reaction, exothermic reaction. We emphasize the fact that yes, using the Hess law, following the Hess law, that you need to calculate different. You need to know the heat of formation for different components or compounds involved in a process in order to estimate the heat of reaction of an entire process. And also following the Hess reaction, we saw that certain processes, many processes occur in steps. In some other cases, you actually just take the steps as hypothetical. You look at the reaction and you break it down. So meaning that it necessarily doesn't occur in steps, but you can break it down in steps hypothetically. So we saw all those yesterday. So we'll just be consolidating the theory, what we saw yesterday, by looking at some examples. And I'd like you to carefully follow. And please, if there is any query, remember to use in the panel, remember to use the reaction icon. Where you raise your hand, and if you want to unmute yourself, you can do that as well. So you can raise your hand, and once I recognize you, you can unmute yourself. And if you want to rather type the question in the panel, you can do that so that I can attend to them afterwards. So I'll go through them, and then we'll then attend to that appropriately. All right. So I haven't any question before we move on? Yes. So in this way, yes, the recording will be made. So and then it will be uploaded. So for every class we do synchronously, recordings are made and will be uploaded. Any other one? Okay, so let's move on. So calculate the standard heat of reaction for the following reaction or for the following process. So if we are to look at this, we have compounds. HCl is a compound. So we have, so give me a moment, please. So we have HCl as a compound. We have water as a compound. And then we have, for the others, water will take this as elements. So you remember from chemistry, for the compounds, you have different elements coming together to form, a compound. So we have those two compounds. So let's start by looking at how to solve that. Another thing that is very critical is this. The states are not put there, for nothing. It is essential for you to take note of the states of the different compounds. So look at this, it's gas, it's gaseous. So that is gaseous, this is gaseous, meaning it's steam. It is essential to take note of that, because whenever a compound or whenever a compound, a substance, it's in a different state, it has different characteristics. It has different properties. So that is why it is essential to take note of those states. All right, so let's move on. So calculate the standard for the following reaction. So we've said, as I've mentioned earlier on, we've noted the compounds and we've noted the elements. So the compounds, HCl, and then and water or steam, water in its gaseous state. And we can only do this by looking at the heat of formation for the different components. And if you remember from your Hess law, and from the process, from the equation we looked at yesterday, we said that you get your heat of reaction by summing the heat of formation for the products and heat of formation for the reactants, and then you find the difference between the two. So it's not, so the summation, you do that. And then another thing that is critical is the number of moles, the stoichiometric moles for those different components. So having said that, let's look at our table, which you've been provided with. So we need to look at the compounds in the table. So we're looking for hydrochloric acid. So if you look at that, hydrochloric acid, so we have it there. So we have the heat of formation at, and remember, it's at 298. So 298, heat of formation at 298. So we've got that as minus 29307, minus 9392307. So also take note, it's in the gaseous. So remember the state as well. So we have it in the, so we've got that. So 92307. What else? What's the other compound we are looking for? Water in its gaseous state. So if you look at this, you see you have water in two different states, but we are interested in the one in the gaseous state. So we take that value as well, minus 241818. So if we go back to our question, so what we just need to do now is plug in everything. So the number of moles and then the values. So we've talked about the fact that the number of moles are given, I mean the values are given per mole. So that is why you need to ensure that in your calculations you incorporate rather the number of moles, the stoichiometric number of moles. So we have 4 for the HCl, and then we have 2 for water. 4 for HCl, 2 for water or steam, since it's in the gaseous state. All right, so moving on. So we have that I've indicated. So we have M. So we have M for the chlorine, it's 4. M for, we're talking about the number of moles now. So here we are talking about the number of moles. So the stoichiometric number of moles, stoichiometric or theoretical. We call it theoretical or stoichiometric number of moles. So we have those values. So if you put those in the equation we've been given, so you remember we have the products, let's go back there, products and then reactants. So if we put in the products, we have the values for the products there, the HCl. So we have that. Remember, for elements, it's 0. So 0 for elements. So we have that 0 for elements. So we plug in the value for our HCl, we plug in the value for water, HCl and water, if we remember. So HCl in the product, in the reactants, water in the products, water in the product. So we've done that, water in the product. So 2, 4, let me ensure we get that right. So 2, 4 is for, yeah, so that's for water, not HCl. Is for HCl. So I hope you're still following me on that. Okay, so that's how we plug that in, and then we arrived at that. So obviously looking at this, it's an exothermic reaction. Are we all clear on that? Any question before I move on? Questions? Okay, tutor, no, okay. Can I just take some coffee? Thank you, guys. So let's move on. So that's how we arrived at that one. So for 13.1b, there are 2 ways for calculating that. So what I've done is to show you the two alternatives. The very comprehensive alternative, you see that in the note or solution, quite comprehensive. And then I'm going to show you another route. So the comprehensive route, I've put in the different explanations for you to follow through. But I'm going to show you another route, which is a shorter one. I'm sure most of you will be interested in that, but it's essential. I will advise you also look at the long route as well, so that the descriptions, the notes that are made, you'll be able to grasp, one or two things, you'll be able to glean a couple of things from there. So the question for this, for 31.B is that we should, let's calculate the heat of formation of methane. So we are interested in methane this time around. Heat of formation, calculate the heat of formation of methane gas from the following heat of combustion data. So remember, whenever we talk about heat of formation for individual components, we talk about heat of reaction for the entire process. So looking at this, you see there that our methane so we definitely can't use equation 1 to do that. So we have equation 1, 2, 3. So we cannot use equation 1 only to estimate our heat of formation for methane. Why? Because the methane, you can see, it's not in the product side. It's not in the product side. It's not the main product. So for this reason, we cannot. So for that reason, we cannot use equation 1. It's essential for us to use all the equations. That is why they've been put there, and it will make sense why. So let's start by looking at this. You see in equation 1, we have CO2 being formed. So that means if we can get the heat of formation for CO2, we can be, we'll be able to estimate the unknown. So we have, and fortunately for us, from what we have the heat of formation for CO2 from equation 2. And also remember, H2O is also part of that. So we also have heat of formation for H2O. And remember, as I've said earlier on, the states are very important. So for example, if what we have in equation 3, if it were to be liquid, and the water we have in equation 2 were to be gas, we wouldn't be able to use that. But in this particular case, they're in the same state. So that's why we can use that. So let's move on. So I've said we cannot use equation 1 only to estimate the heat of formation for methane, because the methane is on the reactant side. So we cannot do that. It's not the main product. So in equation 1, so if we use equation 1 to look at our heat of reaction at 298, so we'll have heat of the entire, remember, it's the entire reaction. So we have that value, which is there. And then we need to look for the heat of formation for CO2, since that is in, remember, from our, from the S law, from the previous calculations we've looked at, you need to sum the heat of formation for the product minus heat of formation for the reactants. Yeah, so for the reactants. So we have to do that. So that's how we've got this. So that's what I've written out here. Heat of formation for CO2 plus that of water minus that of methane plus that of oxygen. And so if we take that down, so we have that value there. So heat of formation of CO2, we got that from equation 2, 398.78, 398.78. So we have that, which is there. Heat of formation for what else? Of H2O, we got that from equation 3. But remember, as we've said, this is per mole. And what is the stoichiometric mole for water in our main reaction? 2. So that's why we need to ensure that we multiply by 2. And then we have the heat of formation for the CH4 we are looking for. And for oxygen, remember, we've said it's usually 0 for elements. So that is that. And once you calculate, if you do the sum and the rest, you get minus 74.9, 74.9 kilojoules per mole. That is the heat of formation. So let me just re-emphasize. When you, for components, you talk about heat of formation. Components in a process, compounds in a reaction, talk about heat of formation. For an entire reaction, we talk about heat of reaction or the enthalpy. Enthalpy. Any question before we move on to the next one? Okay, so I'm taking that as all clear. So example 13.2. So please, I want us to be very attentive as we continue in this. It's very, because there are some salient points that will be made. So for the following reaction, the standard heat of reaction at 298, remember, as we've emphasized, we will always work for standard processes, we always work at 298 Kelvin. Is 164 point. So you might want to write that somewhere if you're following, if you've got your notebook or something. So the heat of reaction, that is that. And we have for the entire process. So that is for the entire process. The heat capacities, see, P, if you remember, we saw this yesterday, excuse me, relating heat capacity, temperature, and enthalpy. So we looked at how can we relate heat capacity, temperature, and enthalpy. So how do we relate that? We saw that yesterday, and that is what this is looking at. So if you look at this, so we've got for the reactions, we have the components, so CO2, 4H2, water, CH4. So we've got that. And then, excuse me, so we've got all those values there. And then we've got these different coefficients, the alpha, beta, gamma. You have those which are for this. So please take note of that, because we'll be, so that means for each of these components, they have these different coefficients that feed in to this equation. So let's see how we are going to solve that. So take note of the table, and also take note of this. So take note of the table, take note of the formula. So take note of the table, take note of the formula, and also you want to take note of the, so it's a table, is the formula we've been given, and also the value for our heat of reaction that has been provided. So let's move on. So 13.2. So we have that. So remember, yeah, so we have this in the slide. So remember, we are given this, we have that in the slide. So remember, I mentioned earlier on that we want to, in the slide, we looked at the dependence of heat of reaction on temperature, and that is given by this. That is given by this. So you see that the different coefficients that we saw are indicated there. So you have the alpha, beta, and then we have that there as well. And then we have that's the gamma, and then we have the temperature. We have the temperature, which is your T value. So take note of that. And then similar to how we've been looking at heat of reaction, take note. So yes, heat of reaction, where we look at products, summation for product minus that of reactants. We are going to do that for the constants, for those coefficients too. Is that clear? Remember, when we're looking at using the Hess law, we said when you're dealing with the reaction, you sum everything for the product, you sum everything for the reactant, and then you find the difference. So we do the same thing for these constants, the alpha, beta, and gamma that we have there. So for the alpha value, so take note from the table. So that was why I said, write it down somewhere. So for the table, the alpha value for water is 29.16. Alpha value for CH4, 13.41. So if you follow in the table, alpha value for CO2, 26.75, and then for 4H2, 26.88. Remember, in this particular case, we are dealing with these values, we are not dealing with that. So since we are not dealing with this, so that is why you cannot say that, but hydrogen is an element here, so it should be equal to 0. No. So we are not dealing with this. We are dealing with the constants. So that is why we cannot make that to be 0. So take note of that. So that's how we did that. So we got the same way you did that for alpha, you're going to do the same for beta. So to remember, so the same equation, we look at the products and then the reactants. So we've done that for all the, so we do that for all the, processes. So take note of that. I mean, for all of them. So let's move on. So is that clear how we got alpha, beta, and gamma? So we've got our alpha value, we've got our beta value, so we've got our alpha value. So you might want to write it down somewhere as well, 62. So for our alpha, we've said change in alpha is minus 62.54. Our change in beta, we've said is 46.35 times 10 raised to the power minus 3. Change in gamma is minus 7.21 times 10 raised to the power minus 6. Please, I cannot overemphasize the ensuring that you incorporate the number of moles, the stoichiometric number of moles. I cannot overemphasize that. So now that we have those values, we also have the equation that we've been provided with. So all we need to do now is remember this equation from what we were given in class. So we have this equation that were given in class, and then, so let's move on. Yeah, so there, so we now just put in our values. So we are putting in, this is the alpha, change in alpha value. This is the change in beta value. And this is the change in gamma value. Are we still together? So we plug that in. So so for standard, remember we said once it's for standard temperature, standard, we showed that yesterday, that when you're dealing with standard enthalpy, standard heat of reaction, we use that. So that is for the standard. So we've got this, we're looking for that. So we plug in, so the T is 298. So if we plug in there, so our T value has been plugged in, take note of that. So we've plugged in the T value. So if we plug in the T value, we should then be able to eventually estimate our change in H prime. Is that clear? Any question before I move on? Are we all clear? Can I get some responses just to make sure that we are following? You can give responses. Yes, thumbs up, all clear. Thanks, Tuto. All right, so yes, sir. Thanks, Lifa. Okay, so we'll move on. All clear, Matthew Ngubani, thank you. All right, so thanks for that. So let's move on. So that's how we got that. So we'll move on, and then so that is our change in. Okay, so we have on substituting that, we have that. So let's move on. Okay, so to calculate the heat of reaction at 7, so remember the question is calculate the heat of reaction at 773. But what have we done? We've calculated at the standard. At the standard is given, which is 27 at 298. So now what do you do for at 773? It means that where we've used 298 before as our T values, where is that again? Where we've used 298 as our T values, we'll now be using 773 as our T value. So that's what we do. So I believe that should be. So if you look at it, it's straightforward. You just need to take note of those simple things. You need to know what equations you'll be applying. Otherwise, it's simple, but you need to remember the issue of the moles, the simple definition. That was why we spent time yesterday to define those different concepts, to look at the law guiding this, and to guiding this entire process. We looked at the Hess law. So that was why we took our time on this yesterday. So I'm taking it that 13.2 is all clear as well. So let's look at 13.3, question 13.3. Calculate the theoretical flame temperature. This was the last part we looked at yesterday, the theoretical flame temperature. Just let me, I have my note here as well. So the theoretical flame temperature, in some cases, you see it's also called the AFT, AFT for that. So calculate the theoretical flame temperature for carbon monoxide when burned with 100%. So that is given for a reason. When you say something is 100% excess, any taker in class, what's the implication of that? 100% excess. So for example, I say that I've given you you've gone to the shop, you are given your change, you are given the change in 100% excess, or you paid 100% excess. What's the meaning of that? Any takers in the class? What's the meaning of 100% excess? When the reaction is completed, there will still be air left, okay? But that will be left. But now we are talking about, you're right, John Matthews, but from the beginning. So John Matthews is saying it means that there'll still be some air left. That is right. But I'm now talking about from the input side. What is the meaning of the 100% excess? So 100% excess, you've talked about it from the output side. From the output side, I want us to look at it we'll start from the input side, from where you are adding. Remember, if it says you're burning in air, so that means you're adding. It's part of the reactants. So from what you said, you're right, it will be also present in the product. We'll see that as we do this solution in a moment. But I'm also talking about from the reactant side. Okay, so if there are no takers, let me just give it away. never runs out. But remember, you can't, you're saying exact amount of up in the air needed to, okay, all right. So when you say 100%, so that was why I used the example, because if you were to look at all the answers you've given are right theoretically, but that was why I used an example for example, you have, thank you, Clive. When the stoichiometric amount of air to CO is doubled, thank you. So that was why I used the example of change. You're given some money, you know, when you go to the shop. So that means you've been given double. So it is double. So that means the amount of air that is going in is double. But everybody that has attempted, you could see there is a truth in your attempt. But I've shown the flaws in. So take note of that 100% excess air. So also the fact that was made that something will be left over in the reactant. That is true, but we're starting from, yes, in the product side, but we start from the reactant side, in the product side and then the reactant side. When both the reactants are at 373 Kelvin, take note of that. The heat capacities may be assumed constant at, so heat capacities, what is heat capacities? Remember, those are CP values. Heat capacities, those are CP values. So, excuse me, so please write those down somewhere. CP for CO, for O2, and for N2. So for CO, 34.83, 33.03, N2, 53.59. And then the standard heat of combustion, so that would be a change in H naught at which would be minus 283.178 kilojoules per mole. Another thing is, please also remember unit, consistency of unit. If you are to look at the unit here, we'll see there is a commonality in this. We have joules here, we have joules there, but the joules here is in kilo here. So take note of that as well. So those details are very important. We've taken note of the 100%. You're all right about in the product, in the reactants. So we've cleared that out. So let's move on. 3.3. So from the question, also take note, yeah, another thing I don't want us to miss out from the question is this part. It says choose a basis of 1 mole for the C carbon monoxide, a basis of 1 mole for the carbon monoxide. So let's move on. Yeah, so we have that from the question. We have this equation as well. So also remember, another thing I think I need to emphasize at this point, this is where your chemistry knowledge comes in. You could see that every time we talk about thermodynamics, there is a fusion of chemistry and physics. So that's why you see, you must have alluded to this already, or you must have seen this in your in chemistry, in thermochemistry. It is essential to ensure that your equations or your reactions are balanced. Are we still together? So we have this reaction. And remember, because we've been told 1 mole of CO, so that is why we have this equation. Otherwise, what you would have typically written would have been 2CO plus O2. So would have been that gives 2CO2. So we would have written that out, right? But so just remember the basis. So that's why we have this. Another thing is this, another general knowledge. So we'll start with general knowledge. I'm sure by now, this is general knowledge to every one of us. Remember, it says air. But in the air, what exactly is carrying out combustion? What component of the air is carrying out combustion? Class, what component of the air is carrying out combustion? Remember chemistry, We need combustion for the, we need combustion, thank you, oxygen. Thanks, John Matthews. We need combustion for the flame to be produced. Without combustion, you cannot have the flame. So take note of that. So that's why we started. So all these are very important. So air is, so it's 21% of the air that is actually going into, is 21% of the air that is going, that is used for the combustion. So that's why we need to incorporate that. We'll see that. I will see that later on. So take note of that. And then if we relate that to nitrogen, so 21% oxygen, the rest is nitrogen. So take note of that. And then from what the previous thing we talked about, the meaning of 100%, I've just written that here. But all we might have just said is just times 2. So times 2 of 0.5 mole. This is a number of moles here, stoichiometric number of moles. So that is how we've got that. And also another thing I want you to note, which I've written here, remember oxygen is just a component of air. I've talked about that. So that is why we've looked at, so, and remember that part, we'll see, we'll speak to this here. It's just a component, nitrogen is still involved. And O2 is responsible for the combustion. We've talked about that. So that is why we did this. And then for the nitrogen, we need to use that relationship, 21%, 79% nitrogen. So that is why we've got this 79 divided by 21 in relation to the oxygen. So with the oxygen we've got there, so now we have these moles. So please take note of that. So in terms of the reaction taking place, remember, this is not reflected in the equation. However, if you look at everything we've been given, nitrogen is involved as well. The only thing now is the nitrogen is unreacted. Please take note of that. It is involved in the reaction because it is air we are using, but it is not involved in the reaction. It's just like talking about catalyst. Whenever you're dealing with a reaction, in as much that the catalyst just mediates the reaction, it doesn't participate as part in the reaction, but it mediates the reaction, you still need to ensure that you consider it. So the nitrogen will need to consider it. So that is why we've calculated the number of moles there. We cannot discount it, that no, since it is not the one burning the process, we don't need it. But we need to incorporate that, similar to one of the comments you made earlier on, that because the oxygen is in excess, it will still be present in the product. So same thing for the nitrogen. So the nitrogen is unreacted. So the nitrogen will be present in the reactants and it will be present in the product. So let's move on. So typically you want to draw a diagram like this. Take note of this diagram. It helps us to be able to visualize what is happening. And please take note of this carefully. The reason why I'm saying this, it is essential. Let me open the question again. Because if you look at the question, you see that the combustion is taking place at 373. The combustion is taking place at 373 there. So this is where the combustion is taking place at 373. Take note of that, or the flame. But remember that when we're dealing with standard heat of reaction, at what temperature does it occur? At 298 Kelvin. So when you're moving from higher temperature to lower temperature, what do you say is happening? A cooling is happening. Excuse me. There's a cooling happening. But also remember, in terms of our standard heat of reaction, we can only do that at 298. So that is why we've drawn this. So the reaction, so we start by cooling, and then you have the flame formation occurring there. So please take note of that. And then we're going to have, so the difference between this point and that point that is there. So this is where we are going to, we'll be using, we'll be looking at that for the calculation of our T flame, or what is happening for that. So please take note of those things. All right, so let's move back to, what we've talked about earlier on. So we have 1 mole of oxygen coming in. We calculated that. 3.76 of nitrogen coming in. We calculated that. Of CO, remember from the question, use 1 mole of carbon monoxide as basis. So we have that. And then on the other side, remember we have CO2 being formed here. CO2 being formed, how many moles? 1. So 1 mole of CO2. On the product side, we have 0.5 mole of unreacted O2. I hope that you still remember that. We put in from our calculation, we said it is 1 mole. We calculated that because it says it's doubled excess, so we saw that it's 1 mole that came in. But if it's 1 mole that came in and it is half mole that was required to combust 1 mole of CO. So it means that we'll still have in the air that is going out, we'll still have 0.5 mole of oxygen left, and we'll still have, since nitrogen is not participating in the combustion, we'll still have 3.76 mole of nitrogen in the unreacted. So that is why we've got that and this. Is everybody still with me? So we have that, the reaction taking place. Remember, heat of reaction, standard heat of reaction, it occurs at what temperature? 298. But we've said our combustion is occurring at what temperature? 373 Kelvin. Let me pause there to see, just take if there is anyone that needs clarification on this. Are we all clear on that? So I want you to just quickly take that in and see if there's something you need clarity on before I move on. Are we clear on that? Is there something you want me to repeat before I move on? Class? Okay, I've gotten an all clear, one all clear. You can also, you can put a chat, you can put a thumbs up just to show me that you're following. So please, so that is how we got that. I'm sure you can also go back and play the recorded video. And please, as I keep saying, after you've gone through all this, come back and consult me. And also please, the 2 class reps have been working hard to ensure the body system flies. So please cooperate with them so that the body system, in terms of group discussion and the rest, we can fly with that. And the other thing that I want us to do with the body system is, once you have it flying, I'll also be able to, I've been able to secure one tutor. So I'll be able to, apart from you consulting me, so you'll be able to consult me, you'll be able to consult your peers, you'll be able to consult a tutor as well. So that is why I want the body system to fly as soon as possible. It's been 3 weeks now. We need to get it finalized by this weekend so that it flies latest by next week. All right, so I'm going to take it that everyone is all clear. So that is how we got that. So going back from from what we've been given, we have this equation too. So remember, as we keep saying, you look at what you've been given, what you have, look at what you've been given, what you have, identify the right equation to use. So we're dealing with heat or flame in this particular case. We've been given heat capacity CP, and then we're looking at, we have change in temperature, we have that. So remember, let's just plug those in. So we have calculate the enthalpy of cooling. So at the reactants. So how do we do that? Remember, we've said M is for the reactants and N is for the product. So let's look at that using this equation. So all these equations have been provided. It's just for you to identify the appropriate one. So changing, we're looking to calculate the change in heat of reaction. So M mole for the reactant 1, carbon monoxide, reactant 2, oxygen, and then nitrogen. So we have that. So remember again here, in this case, we are remember we are not using standard heat of reaction. Please remember that. We are not using, it is when we have this one, let me go back there so that you don't confuse it that, but you've told us that it's always 0. So remember, we looked at it here, it is not 0 when we're looking at using this equation. We've also seen, we said it is only when you're using this. Let me get to that equation again. When we are using this, so when we're using this, that is when for your element, it is 0. But when you're using the other ones, other equations available, no. So please, because it's not standard heat of formation we're using now. So it's not standard, we didn't use standard heat of formation here, no. So in this case as well, we are not using standard heat of formation. So that is why you can put it as 0. So we, let's incorporate what we have. So 1, number of moles, 1. We have, remember, I said you should write that down earlier on. That is CP, heat capacity for carbon monoxide, heat capacity for oxygen, heat capacity for nitrogen. And then change in temperature. Remember, when you're looking at a change in temperature, how do you look at that? It will be the final minus the initial. What is the final? 298. Because that is whenever we are dealing with heat of reaction, the reference point is usually 298. So everything needs to be taken back to 298. So in this particular case, what is happening? Cooling is happening. So that is why you see that our change in T is minus 75. So, and then we arrive at that. So please take note of that. So the cooling heat of reaction taking place here, but we still need for the change in this, in terms of taking it to the flame. Are we still all clear? So that is why I said having a visual representation is going to help. Taking it to the flame, so we need to have that. I think I've also written down something here for you too, just to remind you that we have this. See slide 17 of the lectures of chapter 13 lecture slide. Also remember, we've said, I've also put a note here that remember this is the standard at so we do that at 298 Kelvin and at 1 atmosphere. So that is why we needed to do this. All right, so let's move on. But for this other part, so for in terms of, let me go back to the question. When both the reactants are at 373 Kelvin, so the reactants are 373 Kelvin. So the reactants are going into the reaction. So they are coming in at 373 Kelvin. But for them before it gets to the point of T flame, it needs to be cooled down to the standard 298. So that is what we've got there. So we still don't have this. So in order to do that, similar to what we did here, we are going to do it here. Even before we calculate this, what do you think? We've not calculated it yet, but looking at what we've drawn here, what do you think would the T flame, would it be higher or lower than 298 before calculating? We've not, looking at what we've drawn and trying to make sense of the fact that it's a flame. So would it be higher or lower than 298? Any takers on that? So because it is always essential to be able to conceptualize these things so that whenever you get your answers, you'll be able to say that, no, this can be right, this must be, this is right. Would it be higher or lower? Okay, I don't see any response there. So I'm just going to move on. So we plug in the values as we did earlier on. So we have the same thing as we did up there. So plug in all the values higher. Thank you, Ngubani. It will definitely be higher, but we'll see it later on. So we plug in those values just as we did earlier on. So we do 50. So we do CP at the CP for the products. So products from 298 to flame. So remember, we did reactants to the products. This is, let me write here, reactants. It's getting, everything is getting packed now. So that's why it would be good if you can have your own note. Reactants to products. So this is this point. The second point here is, so this will be cooling. Then this will be products to flame, or the adiabatic, the combustion at the under adiabatic condition that, as we said earlier on. So let me just color code that. So this is cooling. And then the question talks about, let's look at that. Maybe assume, so the theoretical flame temperature. So this is the at flame combustion. So this is that. So take note of that. Cooling here, combustion there. So same, so at the combustion level, so it's products to flame, product to flame. So everything we plug in here will be for the products. So nitrogen, and we then do T. Remember, this is change in temperature. Change in temperature, final minus initial. So we started from 373, we took it to 298. Now we are taking it from 298 to the temperature of flame. So then I think, okay, I've indicated there, T flame, okay. So if we now we'll just be playing with a general maths. So from here we have this value. So we have a change in H1. You can write that down somewhere. We have a change in H2 by this equation. We have this as well. If this, you'll find this in your lecture slide. But from what we've calculated here, we have this equation 1. So we have this, we can call it equation 1. You can call this equation 2. So you can rewrite this. You can rewrite your equation 1 as this. So if you rewrite your equation 1, you take this value there, then you have plus 581 that, and then you have this. So you have that as we move on. So let's continue. And then if you now substitute equation 1 to 2, so we want to substitute, all the values. You remember we have change in H2. So once we have this value, we remember we can then equate, we can plug this here. I hope you've seen that. We can plug that here. And when we plug that there and everything, we come up with, and then we come up with that, another equation. So this is just about substitution. So you're substituting here. So if you substitute the value, we have the value of change in H1 already. If you plug that in, we do all those calculations. So we have that. But also remember, as I've said, I mentioned that right at the beginning, consistency of value. Since we have the CP in joules, ensuring that everything now is in joules. So we've converted that. So please ensure, I cannot overemphasize that consistency of unit. So if we are to plug that in, then our T flame will be 1,882, 1,821, yeah, Kelvin. Can you see the sense now that, as I mentioned earlier, would it be higher or lower? So it's obvious, that it will be higher, and we can see it is higher. Any question? Questions? Questions?